Hello students, my name is Sumit Sagar Hota. I am a PMRA PhD scholar, IIT Palakkad. Today we discuss the lecture number 26 to 30 by Professor Ashok Desar, IIT Kanpur, of the subject Turbulent Combustion Theory and Modeling by NPTEL. This is the week 6 of the live discussion section. Okay, and in this section we can solve some of the problems and some of the mostly in this week the problems are taken from one website named sanfoundry.com, and these are all related to your lectures provided by sir, and we will discuss all the MCQ multiple choice questions, and some are true false question, some are fill in the blanks question in this section. Now, as I already told, all the problems are mentioned are from www.sunfoundry.com, and this is the week 6 of the live discussion, which we cover lecture number 26 to 30 of Professor Ashok Des sir. Now let's start. The first question: shock waves are highly localized irreversibility in flow. Okay. Okay, this is a true false kind of question. Okay, shock waves are highly localized irreversibilities in flow. Is it true or false? Okay, so it's very simple. The answer is true. Okay, the shock waves are highly localized, irreversible in flow. Okay, how you know it's true or false? This is the basic definition of shock wave. Okay, according to the basic definition of shock waves, this is highly localized, irreversible in flow. Okay, irreversible or irreversibility is same thing. Okay, Let's move on to the next question. Normal shocks can be treated as shock waves parallel to the flow. Okay, that means normal shocks can be treated as a shock waves. Is normal shocks is a shock wave or not? Okay, that is parallel to the flow. Okay, they are asking that is the normal shocks can be treated as a shock wave parallel to the flow. Okay, so means that means indirectly here in this question we understand that here the point of this question is it parallel or perpendicular or diagonal or any oblique angle or like that. Okay, so from this question you get it. Okay, so that means normal shocks is parallel to the flow of what, of a shock wave or not, that we have to now get it. Okay, actually this the answer to this question is this is absolutely false. Okay, so normal shock can be treated as a shock wave perpendicular to the flow. That is the correct answer, which is perpendicular to the flow. Normal shocks can be treated as shock waves perpendicular to the flow. Okay, now let's proceed to the next question. Within the mean free path of molecule, flow passes from what? Supersonic state, subsonic to supersonic state, or supersonic to subsonic state. Within the mean free path of molecule. Okay, this is a very good question. Mean free path you should know. Okay, if a one molecule is there, okay, which is in one mean free path, okay, and then the flow can, how the flow will pass. Okay, and it is also, we should note that it's within the mean free path. Okay, so obviously within the mean free path the answer should be, it is from subsonic to supersonic to subsonic. Okay, within the mean free path, supersonic to subsonic. Okay, within the mean free path of molecule, flow passes from supersonic to subsonic state. Okay, this is the answer. Okay, now next question. When flow passes from supersonic to subsonic state, pressure increases, velocity decreases, both of the mentioned and all of the mentioned. Okay, now both of the mentioned means pressure increases and velocity decreases. Yes, and that is the correct option. Okay, when flow passes from supersonic to subsonic, okay, then the pressure will increase. Okay, supersonic means what? Flow passes from supersonic to subsonic. Subsonic means what? Velocity will be less. And according to Bernoulli's equation, you know that if the velocity will be less, okay, then what will be the pressure? If you assume it is an incompressible flow, okay, I know it's not going to be incompressible flow, but we can assume it. Okay, so if you assume it, then it is the case. Okay, and if there is no assumption, nothing given, you by default you just assume it and do this question. And is in this question, from the given question we can very easily understand what is going to be the assumption. Okay, pressure increases when flow passes from supersonic to subsonic state, pressure increases and velocity decreases. Okay, the impulse function is given by, so here there is different kind of formula of impulse function is given. Okay, only we have to choose the correct impulse function formula. Okay, here the correct formula of the impulse function is a bit, that is f is equal to p into a density into a into v square. Okay, v square, v means velocity square. Okay, rho is your density. A is the cross sectional area. V is the velocity. P is the pressure. And A is the same cross sectional area. Next question. Phenolene represents the logos of points with same mass, velocity and stagnation enthalpy. Is it true or false? Okay. So the answer will be A. It is true. Okay. And how it will be, I will just write down. Phenolene represents the logos of points with same mass, velocity and stagnation enthalpy. Okay, how? Because phenolene can be represented as H versus 1 by density coordinate system. And what is H? Enthalpy. And rho is the density. Okay. So in this H versus 1 by density, or that is specific what? Volume. Specific volume. Graph if you plot, then we can get this relation that phenolene represents the locus of point with same mass, velocity and stagnation enthalpy. Okay, when you plot in this plot, we can just get all these things. Okay, these things I think already discussed in the lectures. Next, proceed to the next question. The end state of normal shocks must dash phenolene. Okay, is it lie below, lie above, or lie on? Okay, or none of the mentioned. Okay, okay, now you can see the end state of normal shock. End state. Okay, we are not considering any middle states. Okay, so this is a very good question. The answer will be the end state of the normal shock must lie on phenolene. Okay, this is the property of one phenolene, that not property in the Fano lines, we can see where the shocks will lie. Okay, so this is one very good question, that end state of the normal shock must lie on Fano line. Okay, initial state may not be, but end state it must lie. Okay. Now let's proceed to our next question. Which of the following is true about adiabatic flow in constant area duct with friction? Okay, it has constant G, it has constant HO. Okay, or it has it follows the Fano line. Okay, so actually the answer will be all of the mentioned. Okay, okay, now adiabatic flow in constant area duct, which is equivalent to constant G. Okay, why constant G? Because of constant impulse pressure. Okay, these are the regions I am writing. Okay, constant HO. Okay, outlet enthalpy. Okay, because it's adiabatic already given in the question. Okay, and follows Fano line. When is only adiabatic condition only, it will follow the Fano line. Okay, okay, these are the regions. Now let's proceed to the next question. The impulse pressure I is given by different formulas are given. You have to tell that which formula is correct. Okay, that is impulse pressure F by A, P plus density into V square. Okay, P plus G square into density some. Okay, so like that is given. Okay, the correct answer of this question is both A and B. Okay, C weight is not correct. Okay, if you can compare the density rho means kg per meter cube. It is meter per second square whole square. So meter square per second square. P is Newton per meter square. Okay, and what is Newton? Kg meter per second square into 1 by meter square. Okay, so now here you can see this meter square and this one cancel, and this values comes out to be kg by meter second square. Okay, here also same, kg by meter second square. Okay, or you can write down this thing as Newton per meter square or Newton per meter square. Okay, okay. Okay, now let's proceed to the next question. Okay, okay. Next question is relay line represents the logos of state with same impulse pressure and mass velocity. Is it true or false? Obviously, this is a true statement. Relay line locus of states with same impulse pressure and mass velocity. Okay, next proceed to the next question. Navier-Stokes equation describes the motion of what? Solid substance, non-viscous fluid, viscous fluid, or gas. Okay. The Navier-Stokes equation always describe the motion of what? Viscous fluid. Okay. But in assumption we are writing it is a inviscid or like that. But Navier-Stokes equation always describes about the viscous fluid. Okay, describe the motion of viscous fluid. Okay, okay. Stress in fluid is equal to diffusing viscous term plus pressure term. Okay, according to Newton's second law for fluid. Okay, okay. What is fourth number? Okay, fourth number depends on what? A. Flow velocity, external field, and characteristics length. Okay, how it is like that? So we should know what is the formula of fourth number. Okay, fourth number is equal to V divided by square root of GL. That is V. V is the flow velocity. Okay, V is the flow velocity. And G is the acceleration due to gravity, which we can tell that the value is 9.81 meter per second square. What is the value? And no, this is the value, and this is called as external field. Okay, why external field? Because gravity is act as ambient, or it's act as a external field, external to the our system of consideration. Okay, and L is the characteristic length. Okay, next let's proceed to our next question. Continuum mechanics is a branch of mechanics that deals with what? That is kinematics and mechanical behavior. Okay, what is the kinematics involved in that system or in that fluid, and what are the mechanical behavior it can also do. Okay, these two things deals with the continuum mechanics. Okay. Okay, so it can be modeled as a continuous rather than a discrete particle. Okay, now let's proceed to our next question. Which among the following cannot be used as an alternative term for a solenoidal vector field? Okay, the answer of this question is continuous random field. Okay, continuous random field cannot be used as an alternative term for solenoidal vector field. Okay, then if it is cannot, then others are the can. Okay, so solenoidal vector field random field under stochastic process multi dimensional vectors or points on some manifold discrete set of points in space. Okay, this is the different criteria of solenoidal vector field. Now the next question, the Navier-Stokes equation can be used in which of the following applications? Automobile, ocean currents, airplanes, and thermometer. Which of the things we have to choose? The best example of Navier-Stokes equation application is the ocean's current. Okay, ocean current is the best example of this Navier-Stokes equation. Okay, and why is it that we also see, and what exactly ocean current do, and why it categorized as one of the application of Navier-Stokes equation, that we can now see. Ocean currents. Continuous direct movement of seawater forces generated by acting upon the main flow primary horizontal water movement these are the reasons for considering the ocean current to be the Navier-Stokes equations application. Now next question, which among the following is not an example of magnetofluids? Plasma, liquid metals, salt water, or alcohol? Okay, the alcohol is not a magnetofluid. Okay, that means plasma, liquid metals, and salt water are the magnetofluids. Okay, this is the basic property of magnetofluids. You just understand. Plasma, liquid metal, salt water. And why alcohol is not a magnetofluid, that also is see. Alcohol is a organic compound. With hydroxyl functional group. Bounded to saturated carbon atom. Okay. Anti-freeze solution at cool temperature. So you can add some ice cubes and you can also drink. You can see people's. But very high temperature it may freeze. Okay, some of the alcohols may freeze at very extremely high temperature. Extremely high. Okay. Now next question. What is the velocity profile of Poiseuille flow? Okay. The answer is quadratic. Okay. You know what is Poiseuille flow and all these things you know already. Okay. And its velocity profile is a quadratic one. Okay. Okay. Velocity profile for Poiseuille flow. Zero at either side of channel and non zero at middle. Then quadratic equation. Okay. Let's proceed to our next question. What are the Newtonian constitutive assumptions regarding relationship, stress tensor and velocity gradients? Okay. The answer for stress tensor is linear and for the velocity gradient it is isotropic. Okay. And how it will be, we just now see. Okay, answer is A, linear and isotropic. Newtonian fluid. Viscous stresses arises due to its Newtonian fluid. Viscous stresses arises due to its flow. Due to this flow, what? Strain rate experiences at every point. And strain rate related to constant viscosity tensor. Okay. And now we can conclude Newtonian constitutive assumption linear and isotropic. Okay. Okay. Now let's proceed next question. What is the incompressibility condition in Navier-Stokes equation? Okay. Now answer is A. Incompressibility means continuity equation. Continuity equation is delta T equal to 0. Incompressible flow or incompressibility condition in Navier-Stokes equation. Okay. The next question is the velocity profile of the Cote flow is what? Okay, that we have to know. The answer is C. Obviously, so the Cote flow having linear profile. Okay, but with one condition. This condition is not given in the question, but if in this kind of question came into existence or this kind of question asked, then you have to assume this kind of assumptions and then solve the problems. Okay. Cote flow is flow of viscous fluid when one surface moves tangentially with respect to other plate. Okay, linear velocity Cote flow means linear velocity profile. When dp by dx, that is pressure gradient, equal to 0. Okay, this is the condition not written in the question, but we can assume this is the condition. Okay, okay. Now next question. When fluid element moves from one position to another, what type of motion is it? That is linear translation. Okay, linear translation is fluid elements moves from one position to another. Okay, when fluid element moves from one position to another and it undergo a change in its dimension, what type of motion is it? It is linear deformation. Okay, by motion of fluid element, it changes its dimension. Okay, if there is a change in angle content by two sides, okay, if there is a change in angle content by two sides, the average angle of the angle is what? Or the average of the angle is what? Okay, this is the question. Okay, this is called angular deformation. Okay, average of angle changed by the two sides is. Okay, the answer is C. What is the magnitude of vorticity? It is twice the angular rotation. Magnitude of vorticity is equal to twice the angular rotation. Omega is the angular rotation and zeta is the zeta mod of zeta is the magnitude of vorticity. The flow of fluid along the curvilinear or curved path is known as vortex flow. Okay. Vortex flow is the flow of fluid along curvilinear or curved path. Okay. Okay. Now what is free vortex flow? Okay, this is the answer of this question. When external torque is absent, the type of the vortex flow is free vortex flow. When there is no external torque, okay, whatever the flow it exhibited, that is called free vortex flow. No, no external torque. For free vortex flow, there is no external torque. Which of the following is not an example of forced vortex flow? Okay. If something is not a forced vortex, that means which kind of vortex that will be? That will be free vortex. Okay. So you have to just see which case is the free vortex flow, then our answer we get. Okay, and that is the answer D. Flow of the liquid around a circular bend pipe. Okay, if your pipe is there and it is bending, okay, bend pipe is there, okay, then that kind of flow is called free vortex flow. Okay, where there is no external torque. Free vortex flow or not an example of forced vortex flow. Okay, next question. Which of the following is not an example of free vortex flow? That means which is the example of forced vortex flow? Okay. Flow of a water through runner of a turbine. Forced vortex flow. Okay. Flow of a water through a runner of turbine is a forced vortex flow. Which is not an example of free vortex flow. Okay. Equation of motion. Equation of motion of vortex flow does not take into account of what? Centrifugal force. Is it true or false? It's absolutely a false statement. Okay. Because equation of motion of vortex flow does take into account the centrifugal force. Okay. Now, equation of motion for vortex flow, as I already discussed, this is a false statement. Centrifugal force is equal to function of equation of motion of vortex flow. Okay. So centrifugal force taken into account the equation of vortex flow. In the calculation of equation of vortex flow, we can take into account the centrifugal force. Okay. Equation of motion of vortex flow does take into account shear force. Okay. Okay. So for this case, shear force is not taken into account. Okay. So answer is false. Shear force is not a function of equation of motion of vortex flow. Okay. Not taken into account. Okay. Or an irrotational flow having velocity given. Okay. The flow field satisfies the continuity equation or not, that we have to see. Okay. Okay. What is velocity potential? Two x plus 3y minus 4y square plus 8x square. What is u? U is equal to minus del phi by del x, which is equal to minus of del by del x of 2x plus 3y minus 4y square plus 8x square, which gives rise to minus 2 minus 16x. V is equal to minus del phi by del y minus del by del y of 2x plus 3y minus 4y square plus 8x square. Okay. Minus 3 plus 8y. Okay. Now let's apply the continuity equation. Del u by del x plus del v by del y equal to 0. Let's see the LHS part. Del by del x of minus 2 minus 16x plus del by del y of minus 3 plus 8y gives rise to minus 16 plus 8, which is equal to minus 8, which is not equal to 0. So here continuity equation is what? Not satisfied. Okay, here continuity equation is not satisfied. So what is the answer then? Then the answer is false. Okay. For an irrotational flow, what is the relation for the velocity potential? Okay. 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 Now okay, now for an irrotational flow, answer will be B. Okay. B is equal to del phi. Okay. What is velocity potential? The definition of velocity potential is equal to V is equal to del phi. Okay. This is the definition of velocity potential, and this is and depending upon the velocity potential, when we put into the equation of curl of v equal to 0, okay, if curl of v equal to 0, then only the flow will be what? Irrotational. So v is equal to del phi, okay, del cos del phi equal to what? 0. That means, and phi is a scalar, okay. Okay, so okay, so, and that phi is the potential function, okay. Okay, this is the equation of potential flow, okay. Because we know curl of grad of any scalar is equal to 0, okay. Okay, now which of the following which of these equations satisfied the velocity potential equation? Okay, the best answer you know very well is that it's the Laplace equation, okay. Okay, now how it is, so that we can see here. U is equal to minus del phi by del x, v is equal to minus del phi by del y, w is equal to minus del phi by del z, okay. Let's apply the continuity. Del e by del x plus del v by del y plus del w by del z is equal to 0, okay. Now just substitute. Okay, now what we can get? Del I by del x of del phi by del x plus del by del y of minus del phi by del y plus del by del z of minus del phi by del z is equal to 0. Del square phi by del x square, del square phi by del y square, del square phi by del z square is equal to 0, or del square phi is equal to 0, okay. This is what called the Laplace equation. Okay. Okay. Now, what is phi? For this question, if the velocity potential given and what is the value of the velocity component in x direction it wants. Okay. In x direction, that means u velocity it wants the point 2 comma 1 it will the value. That means x and y value will be there, and you just have to substitute this x and y value and then directly get the magnitude of velocity in the x direction. Phi is equal to 2x square minus 4y square plus 8x square by y. Okay. What is u? Minus del phi by del x. Four x minus 4y square plus 16x by y. Okay, 36 meter per second. That means sieve it. What is the nature of flow having a velocity potential? Okay, it is irrotational flow. Irrotational is the nature of the flow having a velocity. If a potential flow is there, okay, we assume it as it is a irrotational flow. Okay, or if a flow having velocity potential, it means that B vector is equal to del phi, which in turn means that it is a irrotational flow. Why? Because curl of gradient of phi is equal to 0. That I already shown in the previous questions. Okay. Okay. Okay, so when you put in this equation, that is curl of grad of phi is equal to, or del cross del phi is equal to 0. Why it's so? Because phi is a scalar. Okay. 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 Now let's go to the next question. If the Laplace equation is satisfied by the velocity potential, then the fluid flows. True or false? Okay. That's what we have to know. Okay. Okay, if the Laplace equation is satisfied by the velocity potential, then the fluid flow is what? Okay. Okay, so obviously this is truth. Okay, that if the Laplace equation is satisfied, then only fluid will flow. Okay, because Laplace equation indirectly satisfies the flow to be what? Potential flow, and satisfy the continuity equation, both. Okay, so that is, what is the Laplace equation? Del square phi by del x square, del square phi by del y square, plus del square phi by del z square, or is equal to 0. Okay, next question. The characteristics of the ideal fluids are, okay, that is fluid velocity is uniform. Okay, okay, ideal fluid means it's a uniform velocity fluid and in viscid, that is what? Shear stress is 0. Okay, which of the following is not a case of ideal fluid flow? Okay, this is the force vortex flow. Force vortex flow is not a case of ideal fluid flow. Okay, then other are the case of ideal fluid flow. Uniform flow, Okay, sink flow and superimposed flow. Okay, these are all example of ideal fluid flow. What is a special characteristics of uniform flow parallel to x-axis? Answer is A. Velocity is constant. Okay. For a uniform flow, velocity is always constant. Velocity is constant in what? Uniform flow. Okay. Okay. Now, what is source flow? Okay. Source flow. This is truth. Okay. Flow coming from a point and moving out in a circular manner or radial manner. Okay, it's called source flow. The sink flow is in which fluid moves radially inward towards a point where it disappears at variable rate. Okay, this is false. Sink flow is fluid moves radially inward towards a point where it disappears at a constant rate, not a variable rate, it is a constant rate. The pattern of streamline and equipotential line is different for a source and sink flow. That is correct statement. Okay. Pattern for streamlines and equipotential lines. Different for source and sink flow. Okay. In free vortex flow, the flow is linear in nature. That is absolutely false statement. Because free vortex flow is circular in nature, not linear. What is the nature of streamlines of free vortex flow? That is concentric. Streamlines of free vortex flow is concentric. Okay. For source flow, the radial velocity increases as we move radially outward, which is absolutely false. Radial velocity is inversely proportional to the radial distance from center of source flow. Or in other words, we can write down radial velocity increases when you move radially inward. Okay. When is air assumed to be incompressible? Okay. Answer is at low speed. To satisfy what? Continuity equation. What? To satisfy the continuity equation. Air is assumed to be incompressible at low velocity to satisfy the low velocity or speed to satisfy the continuity equation. The technique of linear system can be used in non-linear system entirely is absolutely false. Okay. Linear and non-linear system are entirely different technique. The disadvantage of a linear system. Okay. Here answer is D. All are the disadvantage of the linear system. Linear system disadvantages. First, cost is very high. For implementing this. Second, restriction to use by the designer. And most of the practical systems are non-linear. Okay. Now, system non-linearities are taken into account by whom? Okay, not whom, what are the system non-linearity we can take into consideration. Okay, all these things we can see. Okay, what are the types of system non-linearity in proper way we can tell. Okay, what are the types of system non-linearity techniques? First is analytical. Second is graphical. And third is numerical. Okay, these are the types of the non-linearities. And the last question for today section is the superposition theorem is what? Combination of homogeneity and additivity. Okay. So superposition theorem is the combination of homogeneity and additivity. Okay, this is the last question for today. Okay, thank you for attending the section. If there is any doubt, you can ask me in YouTube by in the comment section, and if you have any other doubts, you can ask in our question and answer forum in NPTEL. Okay, and try to attend the live discussion section to clear your doubts as in the subsequent sections. Thank you and good night, and keep solving the problems.